So our next speaker is Dibyendu. So Dibyendu is from Bellefield and he's doing a lot of interesting work. It will be a pleasure to listen from him. So please.
Okay. First, thank you, organizer, for the invitation. So this is going to be a lattice talk, and I'm going to discuss about how one can calculate all this thermal potential at finite density, finite temperature, and also I will talk about some extension how to get the potential at finite density from lattice QCD, which is non-trivial. Okay, so just to motivate, so this picture we have seen today and on Monday. So if lattice QCD calculation predicts that as the temperature increases, that there is a change in the degrees of freedom, as indicated by the pressure if you plot as a function of temperature. And below, so there is a rapid change somewhere around TC, which is called 150, which is around 156 MeV. And below that temperature, the system is mostly consist of gas of hadrons and its resonances, which can be described in the lattice QCD can be described by that. But above that, the system consists of quasi-free gas of quarks and gluons. And as it has been mentioned also that if we go to very high temperature, there is a difference between the non-interacting limit and lattice study. And this is plotted up to like 400 MeV temperature. But if you go to even at asymptotically high temperatures, the difference persists. And this says that this plasma is really non-perturbative even at very high temperature. And lattice QCD is the one of the tool to study this plasma at this temperature range. Okay, so how can we study what are the properties of this plasma? What are we supposed to extract out? So, for example, something has to change. If there is a plasma, and if there is no plasma, something has to change in the properties of the medium. So, for example, if we calculate the static potential that has been discussed, so when there is no plasma, that means we are in the confined phase, the potential is increasing function of R, and it goes linearly at large R. And this is the Cornell potential, and there is a string term in it. Once we go to above TC, this potential gets screened. And if there is a bound state, some hadron or Quarkonia state is supported by this confined potential, may not get support anymore in the finite temperature potential. And this is one of the famous reason of Quarkonia suppression that has been plotted in the experimental. So where these red points are from the what one would get from expect from PP collision, but this blue line is from what is happening in the lead-lead collision in CMS. And we see there is a clear separation from the expectation of proton-proton collision to lead-lead collision, and which shows that there is a suppression and in medium effect on the Quarkonia. Not only that, we also see this sequential suppression, this higher excited state. This is first one is 1s, then 2s and 3s. They get also suppressed. Okay. So this is one of the important property to study this potential and extract out the information about the plasma. So means what is the screening, what is the screening radius, and what is the damping rate of the plasma. Not only that, there are also other probes. Thermal photons and dielectron produced from the plasma is one of the important probes. Then jets that has been discussed. Then there are also some, I think, called screening masses, which is also important probe, which directly probe the non-perturbative aspect of the Quark-Gluon Plasma screening masses. So, and then there are many other observables. Okay, so what this talk is going to be about? So this talk is going to be about this first part, this calculating of this potential. So this is the content of my talk. So I'm going to discuss about this singlet potential, and then from that potential, how can we extract the spectral function of the Quarkonia? Then octet potential, and then I show some preliminary work of correction to this thermal potential at finite density. And this is still ongoing with Jishnu Goswami and Olaf Kaczmarek. And there is also additional corrections to this potential. For example, this potential is same for vector particles, epsilon, or pseudo-scalar particles. The potential cannot distinguish between them. And to distinguish these particles, one needs to add some correction, which is called the spin-spin correction at finite temperature, which will distinguish this vector meson and pseudo-scalar meson. And that you can hear more about this on Friday by Swagatam's talk. Okay, so let's start with this singlet potential. So first, we need a correlation function. So think of, we have a quark and anti-quark pair separated by a distance r prime, and then you propagate it in time, and then annihilate this pair. So what is the energy that gains that gives you the potential energy between them? So to formally define, so we have an eigenstate of QCD, gauge invariant eigenstate of QCD n, let's say. Then I create this, I act on this eigenstate by an operator O, which is this separation, which describes the separation between quark and anti-quark pair at r prime distance. Then I propagate it to up to time t, and then annihilate in that same eigenstate. And then I take the thermal average over this eigenstate to get the what is called the thermal forward correlation function. Okay. So this is the fundamental quantity, and it has all the information of it picks up all the information from the plasma when it propagates through the medium. Okay. So what is this gamma? This gamma is basically looking into the channel. Which channel I'm looking at? For vector particles like J psi or upsilon, this gamma is just gamma mu Dirac matrix. For pseudo scalar is the gamma 5. For eta c and eta b particle, this is important. And not only that, it can be also, for example, if it is singlet, then it's obvious it has to be 1. When you are going to the octet case, then it has to be TA. Okay. So now I want to study the potential between them. So to start to describe the potential, so we have to first, potential is defined in an effective field theory language. So the heavy quark mass has to be much greater than the temperature and the lambda QCD scale. So if you expand this QCD Lagrangian of heavy quark sector, and then you have this expanded version, and there is this standard kinetic term, then spin interaction term. And here theta is the work field, then this phi is the anti-quark field. So in this framework, in this expanded version of this Lagrangian, if we want to look into the propagation, that propagation amplitude that I defined here, then what it should look like. So first, I'm going to the static limit. So m is infinite. So none of this thing, this 1 by m part will go away. So only this first term will contribute, I d0 minus m. In that limit, it can be shown that there is a factor e to the power minus 2i mt. This is expected. This comes from these two quark mass. So if there is no interaction, they just propagate with the total mass 2m. So that is this phase factor. And then there is something extra on top of it that is called a Wilson loop. So the Wilson loop is drawn here. So we have a quark anti-quark pair separated by a distance r. And because they are static, they cannot move into the space. So they just propagate into the time. And after that, sometime they get annihilated. Okay. So if we calculate this Wilson loop, then I have the access to the correlation function in the infinite quark mass limit, and from that I can extract the potential. Note that this t is the real time. Okay. So what is supposed to look like if it has to be a potential like thing? So from standard quantum mechanics, we would expect that at large temperature, equal to infinite temperature, when t tends to infinity, long time limit, it should go like some exponential of minus VRT, and this quantity in the exponential VR is the potential, right? So that is the standard thing. So this is what we would expect. Then if we reverse this equation, and then I can define the definition of the potential as this limit t tends to infinity value of this quantity. So again, I mentioned that this thing is defined in the real time. Now we have to extract this quantity on the lattice, and there is a problem. And the problem is here. So on the lattice, what we calculate is the Wilson loop we can calculate, but it's not in real time, but it is in Euclidean time. So here is a picture of lattice typically. So this is the temporal extent, total how much is the lattice size in the time direction, and that is what is called beta. And the inverse of beta is basically the temperature. So if we have a large temperature, the beta is small. So lattice extent is small. When the 0 temperature, the beta goes to infinity. Okay. On this lattice, we can calculate the Wilson loop. So there is a quark anti-quark pair separated by distance r, and then we propagate it and then again annihilate it after some time tau. So this is the Euclidean time. So that is what we can calculate from first principle lattice calculation. Okay. But what we need is the time which is real. So I have to analytically continue from tau to IT. So the general way of doing this is, so we have a Euclidean correlator. You can write some kind of spectral function from it with a Laplace transformation like a structure. So in principle, you have from this Euclidean measurement lattice QCD data, you have to extract this spectral function in principle. And once we have that spectral function, then you can just do a Fourier transformation to get the real-time correlation function that is required for the potential calculation. So, but calculating this spectral function from the Euclidean lattice data is a ill-posed problem. We cannot calculate it from the Euclidean Wilson loop directly. First of all, we can see that this spectral function is a continuous function of omega, right? It's integrated over d omega. Whereas this Wilson line and Wilson loop has different only finite number of points because we have a finite lattice spacing, right? We do not have infinite number of data points in this time direction because there is a lattice spacing. So the number of points is different. As a result, there is a degrees of mismatch in the degrees of freedom. So we want to extract more information than we have. And there is another problem, which is the error of the correlation function. So any correlation function on the lattice has a statistical error bar. And any small error in this correlation function gets exponentially large when we want to calculate the spectral function. So a spectral function error. So the spectral function error is exponentially large because any small error gets multiplied this e to the power omega tau factor, and that is the reason. So there are infinite number of spectral functions that can go through the lattice data. So we really have to put further physics information on the spectral function to get the proper potential. Okay. So in one line summary, so when you have tried to do the analytic continuation tau from IT, so you have to do the analytic continuation, it's a dangerous problem unless you put a more physics information into it. Okay. So I will tell you what physics information I have used to extract this potential. And as I mentioned here, it often comes from perturbative QCD and effective field theory approach. Okay. So let's try to understand the analytic structure of the Euclidean Wilson loop. So at zero temperature, it's very fast principle. We know that in Euclidean time, this goes like e to the power minus v tau. Okay, it is at zero temperature because you can just imagine this correlator is this Wilson loop is a correlation function of source and sink, and you insert a complete set of state, and at last time the lowest state survive. So from that you can extract the potential. And how can I see in the lattice? So we can calculate something called effective mass, which is the ratio of this Wilson loop at 2 consecutive time slices. And if we plot this as a function of tau, if the pure exponential behavior dominates, then we should expect a plateau because you can just plug this thing into here and you can see it should be a constant. And this is real lattice QCD data. And you see that as you go to tau, after some time there is some plateau kind of structure reached. And so in this region, this pure exponential behavior dominates, and you can extract out the potential from this plateau region. Okay, so this is quite trivial, right? The analysis is just exponential minus v tau, and you can just do the analytic continuation, and you can see that this potential exists trivially. At finite temperature, this is complicated. First of all, if we do the same plot at finite temperature here, this is 110 MeV, but it is 220 MeV, it's in the deconfined phase. You see there is no plateau at all. Okay, so how can I extract a potential from there? Because earlier there was a plateau, we can extract. Now there is no plateau, we cannot extract. So we have to first identify what is the reason of this, what is the reason that there is no plateau at all. And the reason can be traced back to the case, if we look into the leading order perturbative calculation. So this is the diagram that today also discussed. And if we use this diagram and calculate this potential, then you see that this potential is not purely real, it's a complex quantity. There is a real part which gives you the screening in the medium of the potential, and there is imaginary part which is the Landau damping that one can get by cutting this one loop self energy of the gluon. Okay, so the existence of this imaginary part can be traced back to the fact that there is no plateau. Okay, so then in this plot, there is some information about the both real and imaginary part, but we have to extract it properly by identifying the proper Euclidean time structure of the Wilson loop. It's not pure exponential, it has to be something else. So how can we get idea about this analytic structure? Again, we look into the leading order result of this correlator in Euclidean time. So we have this Wilson loop of, and if we just look into the leading order result, then it has a proportionality factor with tau, and there is a periodic part in the potential. Okay, this tau proportionality factor can give you a pure exponential behavior. The fact that there is no plateau is coming from the fact that there is a extra piece which is periodic in tau. Okay, and this structure particularly will lead you to the existence of a thermal potential. So if we see, then if we just calculate this, do the analytic continuation, go tau to IT, go to tau to IT, and calculate this limit, then I can see that in this, if we have a structure like that, then I have a proper real part and imaginary part. Huh. In this calculation, this structure is gauge independent, but you can do also it in Coulomb gauge, and we get the same structure. Only in the Coulomb gauge, only the longitudinal part of the gluon propagation will appear, but in general, in Wilson loop, you don't need to. We can do it, but it's at zero temperature it's okay. You can do fixed, but in Coulomb gauge, at finite temperature, the leading order calculation supports that there is no gauge dependent. The potential is gauge independent. It's same as without gauge fixing, but there is no non-perturbative argument behind that. Okay, so this is particular structure leading order suggests that there is a potential. But having this structure in leading order doesn't mean that this structure will hold in lattice QCD data. But if we plot this quantity, this ratio at tau and beta minus tau, then what happens? If there is some periodic part like structure here, this part will get cancelled out in this ratio because this is just periodic, and only this part survive, and you have a quantity like this. And again, from this ratio, you can extract a quantity A at tau, which is like effective mass version at finite temperature. And if this quantity shows a plateau, then this structure shown in leading order perturbation theory also hold non-perturbatively. Here is the lattice QCD data recently. So this structure has been suggested in this paper. And if you plot this quantity as a function of tau by A, you do see there is a little dependence on tau, and you have a very large range in the tau direction for A at tau for various values of distances of quark anti-quark pair. And this suggests that this structure holds non-perturbatively. Okay, are there any questions? So this is very important for understanding.
So here for the R by A 24, the low tau by A region, the fluctuations are purely statistical, or there can be other sources?
A small R by A is
so the purple,
the upper on this one.
yeah. So below,
I think it's purely statistical.
It's just the sampling statistics.
It's just only sampling statistics. Okay. Yes. If there would have been a structure, you do not see this oscillation, right? You could see a constant trend of going down or up. Now we know this structure holds non-perturbatively. So we now do not write it as leading order, it's a non-perturbative statement now. So again, you can show that the existence of potential hold when this quantity sigma RU goes like 1 by U square, because if you take a derivative with respect, then one of the U comes here and it gives a delta function. To make it finite, then you have to go like this sigma RU have to go like 1 by U square. Following further perturbation theory in HTL, one of the U squared in the perturbation theory comes from the Bose distribution function. So we parameterize this sigma RU as Bose distribution function times some odd function of variable u. And using this, if you plug now this sigma Ru form in this expression, we get a relatively compact form of the Wilson loop as a function of R and tau. So for each values of R, I fit the lattice QCD data with respect to tau, and I can extract out this real and imaginary part of the potential from the lattice QCD data. Okay, and you can see that this fit very well, and with the chi-square per degrees of freedom around 1. So now I'll show the fit, the result of the potential VRE and VIM. Here it is. So this is first, I should give some lattice information. So this potential is still not at physical pion mass. So the pion mass in our configuration is 320 MeV. It's not physical. The lattice spacing is around this Fermi, 0.028 Fermi. And the temperature is controlled by only changing the total number of data points in the time direction, not by changing lattice spacing. So we are changing from 24 to 28 and then 32. And we are gradually decreasing temperature from 293 MeV to 251, then to 220 MeV temperature. Okay, so first, this is the real part from the lattice. So this is the 110 MeV temperature potential. So we see there is a clear string part in the potential, which is expected because we are in a confined phase and the potential should show some kind of string tension. But once we go to the high temperature or plus deconfined phase, the potential starts showing saturation behavior, and we can see this goes down.
What was the critical temperature?
It's 180 MeV, around 1 MeV. And so we didn't calculate it, but we just extrapolate these scaling functions to get it. That's it. Okay. And on the right hand side, I plotted the imaginary part of the potential, and we see that with increasing R and temperature, the imaginary part is increasing. So for a given R, if you increase the temperature, the potential is increasing. For a given temperature, if we increase the distance, then the potential is also again increasing. Okay, so this is the large imaginary part. So this is from lattice. Now I should compare from the perturbative calculation to quantify how much is the non-perturbative effect here. So here is the case. So first of all, the real part need to be renormalized to properly compare with the perturbative potential. So here is to renormalize it. So we have what we have done. We have matched the short distance part of the real part of the potential with the 3-loop perturbative expression. So this curve, this red curve is the 3-loop perturbative expression. Then I have adjusted the additive constant of the real part to bring it to match it here. Okay. There are also some other technicalities involved. This has to be like renormal and subtracted and all those things, but I'm not going there. And you can see there's 2 particle mass, this eta C and eta B mass particle is supported in this confined potential. Okay. Now I use the same additive constant and subtract the finite temperature version of the potential. So it is displaced there, so this continuous line. So this is nothing but the same figure here, just a fit form, and the additive constant subtracted. And this dashed line is the still perturbative prediction of the potential. And we see that there is a huge non-perturbative effect from going from compared to even at 293 MeV temperature. Okay. Again, here there is the imaginary part of the potential is plotted. This is the lattice, and we see this is the perturbative prediction. So it's a huge difference. So in non-perturbative, we suggest that there will be more damping to the Quarkonia bound states. So really lattice calculation is needed for this kind of temperature to get realistic calculation of Quarkonia. Red line is the fit unjust that I will be this some fit unjust. It's not well motivated. Which fit?
Like the red lines which show in the
this is because now we have the potential, right, from the lattice data. Now I want to extract some information about the Quarkonia. So for that, I need to solve a Schrodinger equation, and there I need a parameterization of the potential. So there I will.
So this is not just some functional fit which makes your chi-square per NDF lowest. It's a sort of the Schrodinger's equation functional form you're getting from there, which you...
No. Potential has different R dependence. Then I have to plug that potential into a Schrodinger equation.
Right. Yeah.
Now I cannot just put the lattice data into that, into the Schrodinger equation. I need a parametrization, a continuous function to solve it.
And about the top plot, I had a question. Apart from those error bars from, say, sampling statistics, etc., can there be other sources of systematics which you may need to put on these lines?
At this moment, I don't want to put any systematic on this. So here there are some error bar. I just put here the central value of it.
Right.
But on the real part, there is nothing, no more error can come. No systematic.
No, I mean, it's theoretically, it's exact.
According to this prediction that this goes, this prediction, this plateau holds, this structure holds, it's exact. Okay. But imaginary part, there might be some source of error bar because there is some dotted term there that I ignored. So there might be some source.
Blue line, did I understand correctly? No, the right bottom. Yes, the imaginary.
Yeah.
Yes, the blue line, which is below. There is a blue dash line. What is that? Perturbative result?
This is perturbative.
Which kind of coupling constant do you use there?
It is the coupling constant determined at the scale of pi t.
So what would be the screening mass in this unit, the perturbative screening mass? How would it compare with what you extract from the lattice?
So perturbative screening mass will be m d by mass, you mean, right? Perturbative d by mass.
In magnitude,
It's around GT. So G is roughly, alpha is, let's say, roughly point.
Yeah. I mean, the ratio between what you get on the lattice and the perturbative result depend on some coupling constant. Okay, this is yes. Now, the ratio between the effective mass or the double mass you extract from the lattice and the one in perturbation theory with the same coupling will also be a ratio. Is it comparable to this ratio?
Oh, no. It's much different. I do not have the value of the debye mass I extracted from the lattice. It's in the paper. In this paper, it is given, but I have to check what is the value actually. Yeah. So debye mass is defining debye mass non-perturbatively. It is a little trickier thing. It's defined only in a gauge invariant of way up to next to leading order. I don't know whether it can be defined.
GT in the double mass
It's the leading order case.
G over the 2, right? To make it compatible
order.
with the lattice. So if you would do the same for this perturbative result for the imaginary potential, would you get something close to the lattice fit? No, it would be much smaller.
Yes, imaginary, but it's really difficult to get that much of magnitude. Okay, so as I discussed, so we have to get extract of some of the information of the Quarkonia part using this potential. And the way we did it is just solve the Schrodinger equation. So it's not just something ad hoc. Ad hoc potential that I'm using to solve a Schrodinger equation. This equation can be derived rigorously starting from the action. So I'm not going to do that. But if you solve this Schrodinger equation and calculate this with this initial condition, then after solving it, if you take a Fourier transformation of this forward correlation function, then you get the spectral function. So once we have this spectral function, you can plot it as a function of omega, and this is for the pseudo-scalar eta c case, and this is for the bottomonium eta b case on the right hand side. So we see that first at 0 temperature there is this sharp peak that corresponds to the 0 temperature Quarkonia masses, and as the temperature increases, first of all, we do not see any excited state that survive. There is no excited state that survives there. And there is a huge thermal impact on the ground state part of the eta c, and we see that there is the width of this peak gets broadened, and as the temperature increases, it gets more and more broadening. And when the temperature is around 293 MeV, there is a peak bump-like structure, but it's difficult to associate any charmonium states at this temperature. We don't know what is, it's difficult there. But even in the case of eta B, all these things hold, but the width is much smaller compared to eta C case. And even in 293 MeV, we see there is a clearly well-defined peak for this particle, and this suggests that eta B survives up to this temperature. So the conclusion from this side, it looks like that charmonium melts around 300 MeV temperature in the medium, means the ground state peak. Okay, so this is all about the singlet part of the Quarkonia spectral Quarkonia and calculating the spectral function. Now I'm
just want to understand.
Yeah.
So that delta type.
Delta type.
This sharp line.
So sharp line is basically so if there is no temperature, sharp line is basically a Dirac delta function. It happens at the masses of the bound state. So if this is like, for example, the eta C mass is around 3 GeV, so this happens as a sharp peak at that, a delta function at that.
And then all these temperature are medium temperature.
When you increase the temperature, this ground state peak that gets broadened. That just has the impact from the medium, and this Dirac delta function gets broadened like that.
And what about the second peak?
Second is this is eta C1s, this is eta C2s.
And that corresponding peak you don't see?
No, Lattice suggests that it's gone.
Oh.
It's by this, and this temperature it has, because you expect this has a larger radius, it has get more impact from the.
You don't see even small.
Maybe if we, so it's, as I said, it's the temperature is around 180 MeV. TC is the 180 MeV, and 220 MeV is maybe it's too high for it. If we go to little smaller temperature, there may be some remnant peak, but that I cannot say from this figure.
Same thing here also.
Same thing here also. Probably if we go to little smaller temperature, there may be some structure you can see. Okay. Yes.
How literally should we take these temperature numbers? Are they absolutely calibrated? You have a physical pion mass. I mean, is this a completely physical calculation? And so 300, you really mean 300 MeV, or is this only for some approximation to be improved as the pion mass gets more physical?
Okay, so some improvement will be there. So we are currently trying to do it on the physical pion mass.
What is your current pion mass?
It's 320 MeV.
320?
Yeah.
So rather large.
Rather large, but if you go to very high temperature or this charmonium physics, pion mass is pretty low actually. Charmonium, the scale is around, let's say, a few GeVs, right? Charmonium and bottomonium. So the pion mass is rather very low here.
So the unphysical pion mass isn't important for this number? Or?
Maybe for this physics, it won't change much if we go to physical.
If we write in terms of T by TC, then,
Yeah, then
it should not matter. So if we scale these temperatures in units of T by TC, so here TC is 180 MeV. And as he was mentioning, the medium FS comes mainly in the T by TC scaling. So if you divide 220 by 180, it will be like around 1.2 TC around. So if you want to go to physical pion mass, this will correspond to a temperature 180 MeV.
As you know, T by TC thing can sometimes be confusing. In the heavy quark diffusion case, the various pion masses results fit much better if you do not do the T by TC scaling. I don't know. It could be similar physics, no? I mean, the gluons at 300 MeV, since it's mostly gluon-driven physics, maybe the absolute temperature matters more. I don't know.
There can be logarithmic corrections, right? So that can come.
Can I ask?
Took some questions simultaneously.
Okay. Yeah, I would like to come back on the way you adjust the real part of the potential.
This one?
Yes. Yes. To define the binding energy, we need to compare the energy of a pair of QQ bar inside the potential with the asymptotic.
Exactly, but
okay, and that doesn't concern so much the interior of the potential, but the region where the force stops to act, which is when the potential becomes flat. So how do you handle that? Because I think you adjust the potential in the region of small distances, right?
Yes.
So what is, another way to ask the question is, what is the mass of the heavy quarks at large distances when they are far away from each other? That's affected by thermal effect.
Quarkonia, right? It means the heavy quark mass will not change, but the Quarkonia mass
To change. For the same reason as thermal effects will affect the mass of the heavy quarks, right? So it's a continuum.
But what I just want to understand. So even in the asymptotic case, the heavy quark is not purely a quark-antiquark pair, right? But they has to come with this open flavor state, right? So it cannot be just.
But the mass of these two objects,
yes,
when they are in the medium, is different from the mass that they have in vacuum.
Absolutely, right.
Okay?
Yeah.
How is that taken into account in your calculation and in the renormalization of the potential?
So these two lines you see, so it's first of all, we do not perform the renormalization at finite temperature. We do at 0 temperature.
So then renormalization was inappropriate. But how do you adjust the potential?
Okay, so
you adjust at 0.1 Fermi or something.
Yeah, so you mean this plot? How does this plot come basically?
But how sensitive if you change 0.1 to 0.8 to you wouldn't change what's inside, but you would change the data potential.
Then these two lines you see will be at different value, which is not experimental, you observed. So these two lines is basically what you get from solving the Schrodinger equation and adjusting the additive constant such that it falls into the experimental value. So that is what fixed this to. Then I use that same additive constant to subtract the finite temperature because renormalization is independent of temperature.
Constant is one is for C and unique for B. Right? There's one constant, right? For each species.
Exactly, there has to be one constant. That same constant.
Okay, so forget about the B for a moment. Just the C.
Okay.
If you would change eta C or whatever it is, if you change the grid line by a small amount, it will modify slightly the potential inside, but that modification will be hardly visible. But you can modify at long distance substantially.
Yeah, but how? Why should I move this?
Yes.
I'm not sure I understood, but why do I want to move this line? Because it's fixed.
There is a strong stream tension that is irrelevant, but when the potential becomes flat, that becomes because then the region where the quarks don't feel any force will be.
So what will happen if there is some shift into the potential? So this whole thing will going to get shifted by some small amount on the right or left, depending on the additive constant. That's the only thing that can happen. So everything we can, let's say, shift it by some amount, then the peak appears somewhere else.
Maybe we can.
Yeah, we can discuss it. Okay, so this is all about this. Now I'm going to discuss about the exotic or hybrid potential, from which I will also show about the octet potential. So how much time I have? So I have 15 minutes. Okay. So this is all about the potential in the ground state when we expect. But if we have a quark-antiquark pair separated by some distance r, there can be other channel of interest because there are some symmetry with respect to which you can identify different quantum channels. For example, when the quark-antiquark is separated by distance r, you have some rotational symmetry, and therefore you have some conserved quantum number L, angular momentum with respect to the separation axis. It is 0, 1, 2, like that quantized. Then you have some symmetry with respect to charge conjugation and parity. And then you can have some symmetry with respect to the inversion with respect to a plane. So these are the three symmetries that can be used. So all the quantum state with respect to the symmetries are orthogonal. So the way we create this quantum state, we have this quark-antiquark pair again separated by distance r, and then we attach some operator h to project into particular quantum state. By choosing h, we can get different quantum state. Okay. When h is equal to 1, then we have the standard Cornell potential. And then when we choose some h equal to some chromomagnetic field z component, then it projects to this sigma u minus component. So sigma is 0 and u means this minus. So CP symmetry is giving a minus sign and u and again here. Similar thing. Similarly, we get project to pi u when we have bx plus iby. Okay. So this potential has been studied at 0 temperature. So this is what is shown here. So we see that below at 0 temperature, so at some small distance, we have some repulsive part in the potential. And at long distances, we have this, we have a string tension like a structure, because ultimately total state is gauge invariant and it has to be confined. So there is a string part, and we have plotted these two potential. Here I have also compared this potential with the singlet potential and starting from other lattices. Now notice that the fact that it tends to degenerate at short distance. It looks like they're coming from the same potential. And this is not accidental. And if you calculate this potential, in leading order, what you get is an octet potential, g square by 6, 1 by 6 times g square by 4 pi r. So at short distance, this potential receives contribution purely from octet channel. Okay, so this is our motive. So this is our strategy to study the octet potential. So we study this potential at finite temperature also, and extract out the part which is independent of the chosen operator, and that gives the information of the octet potential. Okay. So this is at 0 temperature, and now we go to the finite temperature. So this is the 0 temperature potential again, and at finite temperature again we see that there is a no attractive part, and as we increase the temperature, the screening became more and more dominant. Here for the BZ channel and here for the B plus channel, similar story holds here. I can also compare.
Yeah, so here, when you go into higher temperature, yeah, right side, the lines become parallel for different choices of DC, right?
Yes.
Yeah, so the difference in this potential, how does it depend on the microscopic theory? Like,
so this is purely temperature dependent. So this difference is because purely MD is controlling the difference.
right. So is there an analytic understanding of the size of the gap, which in the large RTC limit?
So it is the MD dependence of the temp. How does MD depends on temperature that decides this gap? So MD goes like GT.
Okay.
So MD is like, if we consider one loop diagram, it has a G square and T square.
Mhm.
So it just goes like GT.
Mhm.
So that difference, so G times T, that decide this gap. Basically.
But if it's proportional to T, shouldn't this gap increase when you go to larger T?
There is a G also.
So that goes as 1 by T.
Yeah, GT, there is a G also.
So G times T is that quantity T independent?
No, and there is some dependence. It might be smaller, but there are some dependence.
Okay, I mean, by just naked eye, it seems the difference is sort of constant. So that's why I was asking.
When it's constant means between two temperatures?
Yeah, yeah.
No, this difference is larger. This difference is a little smaller. And
What I was asking, let's say for a pair, if you compute the difference, that difference seems to be independent of R times TC.
It becomes flat with R.
Yeah. So what's the physics of that?
I'm sorry, I'm not getting the question.
So let's take any pair of line there.
So let's say I take this line and this line.
Right.
Okay.
So their difference, as you move towards right, becomes constant. The delta, the difference of this.
Yes, it should become constant. Yes.
Yeah. So I was trying to understand what is the theoretical understanding of it, because you were telling this difference should be proportional to GT.
So what I am telling is that, so if you have a potential, maybe I can write, can you see something here? You can see? So if you have some potential here, so you have that for octet potential, I think it should be G4, some e to the power mdr divided by r plus md. So this is like a perturbative expression for different temperature. I'm not sure about all this factor, but so if you just look into two different temperature, so at long distance, this, yes, yeah, system survives.
Going up. So that means like
This one? Sorry.
First line.
Yeah, this one.
Is getting positive, no? If you go to the larger R.
Yeah.
So then it is getting positive. What does it mean?
It's ultimately I am starting with a gauge invariant state, right?
Uh-huh.
So quark antiquark cannot be separated. So that means the potential has to grow up again. So that signifies this.
And negative means it's attractive.
This is attracting potential. This positive slope means it's attractive potential. So here at short distance, it's repulsive. Here it's attractive again.
Okay.
Okay. Now I compare with this singlet potential. Here this again you see this singlet and octet are okay. First two things I should mention here. No, here. Okay, so first two thing I wanted to say that below TC only at short distances these different quantum number channels Bz and B plus are identical. Above TC they are identical at all distances that we have studied in the real part case. Okay, so that means for the real part, we can say that the potential above TC is entirely coming from the octet channel. And not only that, both this octet potential and the singlet potential approaching to the same value, to the same debye mass. And this suggests there is a strong evidence of color screening in the medium, non-perturbative color screening in the medium. Okay. This is for the Cohen's QCD, and this is from preliminary result of full QCD. The more dramatic effect is in the imaginary part. So this is the singlet imaginary part. It should go to 0 at short distance because of this color transparency that was mentioned. But for the case of this hybrid one or this octet one, they go to a finite value. And this signifies that they have a color charge even at short distance. And that is the color octet part. So it's getting damped there. So this is finite. Okay, so this is another. Okay, this is all about the octet potential. Now can I get 5 minutes or 5?
Yes. We have another.
Okay.
Yes, please.
Okay. Okay. So moving towards something about the finite density, these results are very preliminary, but I think this result might be useful for future fair studies or low energy weak energy studies of Quarkonia. The problem at lattice QCD at finite density is there is a harmonic determinant which depends on the complex the chemical potential, which is complex, and therefore we cannot do Monte Carlo sampling, and therefore we cannot directly calculate this quantity on lattice. Okay, this is a well-known problem, and this is the sign problem. So generally what has been done, so people expand around some chemical around some mu equal to 0 and try to look into the coefficient of that Taylor series to calculate it. We would do a similar approach. So again, we have this Wilson line correlator or Wilson loop. We just plug this thing in the standard quantum expectation value. We have this determinant of M. Now we expand this determinant of M or Dirac operator with respect to mu equal to 0. And then we just collect the mu square coefficient of it. And then we have basically the correct second order coefficient of this Wilson loop at finite density. So this is just Wilson loop at 0 times 1 plus mu, a vector which is mu u, mu d, and mu s, and then some coefficient W2. And this coefficient is defined here. Okay. So this is W2 UD is the expectation value of this W with this chi ij, they defined here, minus the disconnected part of it. Okay. So we can calculate this coefficient on lattice because they are all defined at 0 chemical potential. So first of all, I show this correlator W2 UD here. For okay, one thing is technical. So on lattice we have to reduce the error, and I have used some technical gradient flow to reduce this error. Here this correction term is plotted as a function of tau by a for some distance, and we see that this is for SS case at 151 MeV, and we see that gradient flow is really reducing the error. So the 0.6 they are like falling on top of each other. So gradient flow doesn't have much effect, but it's only reducing the error. So I am just taking the largest flow time data points at the moment. Okay. So here I have plotted this delta W by W as a function of tau for various quantum number channel, various quark chemical potential channel, UU, SS, and this cross term. So again, we see that this UU gets more correction than SS. So if I have a quark mass is less, the correction to the potential is larger. And the cross term, US and UD, they are more or less 0. So at the moment, they are consistent with 0. So I'm just not taking into account. Again, I can start with our parameterization and do a Taylor series expansion of our chemical potential and derive a parameterization for the coefficient itself. And from the fitting of this coefficient with this, with respect to with the tau data, we can extract out the correction to the real part and correction to the imaginary part. And here I have shown the fitting for few distances. No, this is just a data. This is I'm fitting. So this is this delta W. See, this is W2 correction. Okay. Now, if from the fit, if I find the real part, and this is the imaginary part, and this is the UU correction, potential correction to the potential due to the U chemical potential, and then this is S. So we see that the correction is more compared to for UU case compared to the SS case, and it's also negative. So it suggests that there is more screening in presence of chemical potential. So it's like almost 50 to 60 MeV shift. Sorry, not 50. There is a half here. So there is a half here. So it's like 30 to 40 MeV shift due to the finite chemical potential into the compared to the zero chemical potential case. And there is again the rising imaginary part, and UU cause more imaginary part than SS. Okay. Now I can just change the basis because in experimentally these are more interesting BQS basis with this chemical potential transformation, and I look into the various quantum channel, and again I see that in the QQ sector the screening is much stronger compared to the baryon sector, and similarly that is damping is much larger for the QQ sector compared to the baryon sector. And this is the static potential. This is the potential without any chemical potential. So to get the total chemical total potential at finite density, we have to add these two things. Okay. So there is a lot of correction to the potential due to finite density, and there can be a lot of effect due to that on the Quarkonia at finite density and low energy beam energy scan runs. Okay, so this is my summary. So I have talked about in medium modification of thermal potential from lattice. We see there are strong non-perturbative effects. We also see that there is a large thermal decay of the charmonium, and charmonium melts around 300 MeV temperature. And I have also shown fast calculation of second order Taylor expansion of the potential at finite density, which shows significant modification at finite density. Okay, so one line summary, lattice result shows that color screening is an intrinsic property of Quark-Gluon plasma that cannot be changed. Okay, thank you.
Thank you, Dibyendu. Any question?
Somehow it seems like the charge particles like pions, they are causing more kind of screening for.
Exactly. So maybe it would be interesting to look into the correlation between JPSI and in the QQ sector in the experimentally also. Okay. Yeah, total finite, total potential.
So does it support? So what am I supposed to conclude? So if you add them, then it supports bound state more, or there is
no. It will support. It will make the bound state more weaker.
More weaker, right?
Yes, because it's negative, right? So for example, this negative. There is one is
yeah, that's what I'm saying. Yeah.
That is BS channel. This is a standard, right? Baryon strangeness, for example, UDS. So strangeness has a -1 and U has a, it has a baryon.
There are color coded. Okay.
Yeah, but it is in the BS channel, but it will contribute like BB term plus SS term minus BS term. So total is positive.
Okay.
Total is negative. So it goes down.
Yeah, I have little bit experimental type question.
Okay.
So Because in LSC or RIC, we have measured Jepsi, and you can also calculate Jepsi spectral function at a given temperature and pion mass. Can you use that? How to match that, and then can you compare with the Upsilon states?
From experimental data.
No, we know that Jepsi suppression is there, Upsilon suppression is there.
Yes, you mean the array you are talking
Not
about?
array, even the spectral function, what you calculate for Jepsi, to know the temperature and use the same pion mass and temperature to get the suppression of Upsilon. Because if you showed the first plot where the CMS result is there.
Okay.
Yeah, so there you can see that almost 2s and 3s is gone. Almost.
Right.
So, but in 2s you can see small peak.
Yes. Yes.
But if you think like in a spectral function, similar thing, what exact temperature and pion mass you can see similar level of, can we do that type of comparison? I don't know. I mean, I'm just asking.
If I understood the correct question correctly, so whether we can compare this spectral function with this directly? The question is no, not directly, because we are calculating at a given temperature and the plasma is evolving and what you get is a net effect of it, right? So to get correct thing, I think we have to convolute this spectral function, calculate the spectral function at various temperature and get a net effect out of it. So that is what I understand.
Okay, we'll talk.
What was your question?
I was thinking how to connect this result to spectral function by knowing the, let's say, Jepsi. Let's start with Jepsi. We know Jepsi.
Yes, you can only calculate from these what level of suppression is expected.
And yeah, that also possible. But okay, so in
of course, this is the in medium SI spectral function. Stuff that you were studying in your database.
So in spectral function, can somebody define like a array type?
No.
No.
No. Means what can you define
No,
array?
I'm just asking because I don't know
So
about.
let's think of, I don't know whether you would call it array. So what is the spectral function?
Or similar.
Maybe you can compare the area under these two things. One is at zero temperature.
Something like
but
that.
I don't know how to connect that to experimental thing because it's something different.
Any other question or comment? If not, let them thanks the speaker once.